scientists are using new technologies to look back in time and recreate how the landscape formed. Bill Dietrich, a professor of Earth and planetary science at UC Berkeley, is a leader in this effort.
This is one of my favorite places on the reserve, and the reason for that is that, in essence, you're walking through time. If you look into this forest and the underlying grass, you see native California as it once was, before the arrival of the European cattle and clearing of land, deforestation, and agriculture. You see the old oaks, and you see the grasses up to my eye height. This is an area that also is an old riverbed. So there's a deeper history here that goes back maybe 30,000 years, when once this was a raging river across here.
The Angelo Reserve has a number of topographic features that had long puzzled geologists. How did flat terraces form in the steep canyons? Why are the terraces so high above the current riverbed? And why are there waterfalls and soft deposits that the river should easily cut smooth? Dietrich and his colleagues are using new mapping and dating techniques to sleuth out the answers. LIDAR, light detecting and ranging, is a laser-based mapping process being refined by the National Center for Airborne Laser Mapping, or NCOM. Based at Berkeley and at the University of Florida, NCOM develops advanced techniques for producing maps of unprecedented detail and accuracy specifically for scientists. The maps are created by flying over the site in a specially equipped plane, shooting a pulsing laser beam towards the ground. As the plane flies back and forth, the laser emits tens of thousands of pulses per second. Computers track the return time of each laser pulse, and technicians later filter through the data to generate the maps.
The maps are revolutionary because for the first time, we're obtaining information on topography at a spatial scale we've never been able to get over a large area. With this technology, you can cover 50 square kilometers in a day and have as much as 4 or 5 data points per square meter. We can see the shapes of hillsides, the shapes of channels, the presence of roads, the occurrence of landslides, and we can actually see the fine details that then allow us to draw interpretations about mechanisms, and also at a high enough quality that we can use such data to test theories that we could never do before. So it would be equivalent to the world having up to now been without glasses. And you function, you can get around, and you can sort of avoid running into trees. You put your glasses on, and suddenly you see so much more. I was completely shocked at what I saw, because the standard topographic maps would use an aerial photograph and the technology then of estimating ground elevation by trying to see through the trees. When the LIDAR data came back and we had the bare topography, you could see that the landscape looked drastically different. Everywhere you look, there are very large, deep landslides that at various times in the past have moved and radically altered the topography. You walk around here and think this landscape is very disorganized, but it didn't make any sense. And as soon as we had this data, you could just begin to see how the landscape worked. And so that revealing, that unveiling, really, of seeing the landscape for the first time as it really looks, as compared to an interpretation, and at a detail that allows us to, propose processes, test theories. It's a revolution, and it's revolutionizing the field.
One key to understanding the Angelo landscape is the fact that it is made up largely of two very different kinds of rock deposits, mudstone and sandstone.
Mudstone is what it sounds like. It's silt and clay pushed together. And sandstone is also what it sounds like. Sand is pushed together. The sand and the mud were deposited together in a deep marine environment millions of years ago by underwater landslides. And that sediment was then compressed and pushed and squeezed and shoved on shore by tectonic processes, eventually ending up where it is now, standing on end like books, with most of the pages in the book being mudstone, but occasionally some of the pages being sandstone. Here is the mudstone, and in my hand I can grind it up and break it. It's mechanically very weak. When it wets and dries, it falls apart. The consequence is the river can cut through this mudstone like butter. In contrast, the sandstone is hard. There are big boulders of sandstone sitting behind me here, covered with moss. All the gravel of the river, all the boulders of the river are sandstone. As rivers cut down in response to the land being pushed up, the land steepens up. And as it becomes steep enough, this weak mudstone simply collapses and gives way and generates huge, deep landslides that flow episodically toward the channel and dump vast quantities of sediment in the river system.
So, if the river cuts through the mudstone so easily, Dietrich wondered, then why isn't its bed smooth? Why would a waterfall form in a mudstone channel?
What happens is the sandstones drop in enough gravel that they armor or protect the mudstone and slow or stop the incision. And what can happen is the waterfall can be steep enough that it can propagate underneath the boulders and the boulders fall over. So this waterfall can slowly migrate upstream through the mudstone and undermine the boulders. And as we walk downriver, we can find emerging from the riverbed rock above our head with sediment on top of it, which records the river at a higher level. And we can walk all the way to the South Fork Eel River. This suggests that this waterfall started at the South Fork Eel River, a couple of kilometers away, and slowly moved up this way. In a sense, unzipping the riverbed, exposing it once again, and then getting mantled again with boulders.
The periodic cutting of the river also has another major impact on the topography. At times, when the river cannot cut through a sandstone mantle, it tends to shift from side to side, creating wide, flat areas. Then, when it reaches the mudstone, it cuts down quickly, leaving behind elevated terraces.
What this points to is a dynamic interaction between the river and the hillslope that's influenced by climate. Now, recent studies by colleagues at the University of Minnesota, in which they've used a new dating technology, have given us dates for the first time of the deposits in these abandoned terraces. And they show that these deposits came in the late Pleistocene, when we know that the climate here was much wetter. And what this suggests is that during wet times, tremendous amount of sediment comes down this river canyon. And there are places here where the deposits are 6 meters thick. And we can find big debris flow deposits, we can find rock avalanches that have tumbled down here. And presently, the climate is much drier than it was during the Pleistocene, and perhaps less stormy. Across this landscape, there are large, deep landslides that are mostly just sitting, having moved in the past but not moving presently. They're slumbering, and they'll be reawakened if more rain comes. And one of our great interests is, will they reawaken when climate changes? Because some predictions have this landscape getting wetter. And is it possible that even in my lifetime, these large landslides that are all over the landscape will start moving again and dumping vast quantities of sediment in? It would not be good for roads, it would not be good for people's houses, but it would be exciting.